All right, well, let's get started this morning back in chapter 9 on the topic of polarity. So whether or not a molecule is polar is sometimes a tricky question. We have to think about, are the bonds polar? And then we have to think about, are the bonds situated in such a way that the molecule picks up a sort of net imbalance of charge? So if you think about PCl5, the PCl bond I think for sure would be polar because phosphorus and chlorine differ in electronegativity. Chlorine's fairly electronegative, so I think we'd have all these individual dipoles pointing out towards the more electronegative chlorine. So remember, N, O, F, and Cl are the most electronegative elements. If you pair anything up with these atoms other than themselves, you're certainly going to have a polar bond, as well as sulfur's fairly polar, bromine is as well. And so there should be a pretty decent sized electronegativity difference between phosphorus and chlorine, giving all these bond dipoles throughout the molecule. But the thought might be, do they all cancel each other out? Another thought could be, is the center of charge still phosphorus? So think about the center of charge. Is the center of all the charges still in the middle of the molecule? If so, that's the sort of dipoles all individually canceling out. So we can usually picture in something like CO2 this happening because we have two dipoles exactly opposing each other that just mathematically or the vectors cancel. There's a lot of different ways you can think of the math working here. You can also think in something like BF3, which is perfectly trigonal planar, the dipoles cancel out as well. So both of these are nonpolar molecules for CO2 and BF3. And we kind of have those two sort of examples with PCl5. We have like a linear bond for the axial positions. And then we have like the trigonal planar equator atoms all canceling each other out as well. So that's why PCl5 would be a nonpolar molecule, despite having polar bonds. In fact, all these molecules on the slide here have polar bonds, so the issue is really just the arrangement of the bonds. Let's look next at octahedral. Because octahedral, it's really, if you can see that on the axial atoms that those dipoles cancel, and then we have two other atoms on an axis, those dipoles cancel, and the same thing for the other two atoms on an axis together. So it's kind of like we have three combinations of CO2 molecules with the dipoles canceling. The center of charge is still that central atom sulfur, in SF6, so despite having polar bonds, this molecule as well is nonpolar. And if we likewise just, why don't we just go through and look at the ones that are nonpolar, because I think the ones that are nonpolar are really easy to see. And the xenon F4 is another one pretty easy to see because we have two atoms on an axis together. We have lone pairs that are on an axis together, and everything's canceling each other out. You might think about the geometry. Remember how we said lone pairs repel bond pairs by more, so the lone pairs might kick these bond pairs down, but this lone pair kicks them right back to perfectly 90-degree bond angles. So in xenon F4, all of our bond angles still perfectly 90, molecules perfectly planar, meaning all five of these atoms are in one plane together, and this molecule is perfectly nonpolar, meaning it has a dipole moment of 0. So the dipole moment in these nonpolar molecules would exactly be 0, because of all those dipoles mathematically or geometrically canceling out. I think there's one other that's easy to tell. That's the xenon F2, the one over here, that we can see these two bonds canceling out. We have lone pairs on the equator of the molecule. And so it's really just the atoms we want to look at. It's the nuclear charge that's predominating, that's giving molecules, if they are polar, their polarity. So it's really just the kind of nuclei we really want to pay attention to and where they're centered in terms of the charge. But they're opposing each other just like in CO2, so we get a perfectly nonpolar molecule. Again, the dipole moment would be exactly 0. And then the other four molecules is they're not situated in such a way that all their dipoles are canceling. So if we just look at the nuclei here, we get an imbalance. So we're going to have charge pointing more in this direction. In fact, those fluorine, the next slides will have the actual bond angles, but the two fluorines here aren't going to be perfectly 90 degrees relative to this central fluorine here. This is going to be less than 90 degrees due to that lone pair bond pair interaction, kind of forcing that axial bond to be a little less than 180, and then that will force those 90-degree bond angles to be a little less than 90. And so we even get the geometry kind of perturbing in a way from the lone pairs, kicking the geometry into a slightly different set of bond angles and perfectly trigonal bipyramidal. And then we also have an imbalance in charge. The charge is not exactly centered on sulfur anymore because we're missing that pole where the lone pair is. So because we don't have a fluorine atom where that lone pair is, we don't have that pull of electrons back off the molecule centering the charge back onto sulfur. So because we don't have a fluorine over here, allows this molecule to be polar. I don't know what the dipole moment is exactly, but it wouldn't be 0. So the dipole moment wouldn't be 0 for SF4. And a lot of these molecules, you can just Google if you're not sure. You can just look up, well, what is the dipole moment of SF4 and kind of see what it is. It's probably around 1 dBi, somewhere in that region there, nowhere near 0. The square pyramidal, BRF5, again, we have a lone pair here. This lone pair is going to kick all these bonds to be a little bit off of their expected geometries from octahedral. So instead of all those bond angles being exactly 90 degrees, they're going to be a little less than 90 degrees. And so then being a little less than 90 kind of is already showing you the charge is imbalanced. So you have an imbalance in charge. You have a more negative charge on the top half of the molecule, and you get a more positive charge on the bottom half of the molecule. So you want this charge imbalance. You want one side of BRF5. So if we flip the BRF5, so the fluorine sticking out is here, the other fluorines are over here, that the charge is heading this way, negative charge this side, positive charge on the opposite side of the molecule. So you want some sort of charge imbalance. You want something like on a diatomic molecule where we had HF as a real simple polar molecule. We get this minus and this plus charge. You get a positive side, negative side. We just want that in our bigger molecules. PCl5, SF6, the nonpolar molecules just have negative charge all across the molecule on every side. There's no imbalance of charge. So the last one are T-shaped molecule, or ClF3. Again, if you just flip the structure, you can kind of see it looks like a T. That's why we would call this T-shaped. In terms of the molecular geometry names, you're just trying to think of the atoms. What's a good name for like SF4? Kind of looks like a seesaw if you can picture the molecule teeter-tottering. So you're just naming the atom geometry for the molecular geometry name. But for our T-shape here, this is going to be a little less than 90 degrees because of the lone pairs kicking those bond pairs further away from each other and then hence closer together. So our T-shaped geometry kind of showing you we get a negative side of our molecule over here and a positive side of our molecule on the opposite side. So the charges really reside more in the nuclei. So when we're talking the minus charge is kind of the nuclear pole. So the nucleus of the atom negatively charged on the fluorine side, on the right side of this molecule, and the left side centered towards the bromine atom, the positive charge. You might think, sometimes we get confused. You say, well, how can bromine be positive yet be centered by 4 electrons that are negatively charged? It's all about charge balance, right? So it's not that those electrons aren't negatively charged, it's that the net charge that bromine has, once we take the electrons away from it, gives it a net positive charge. So it's the impact of the unequal sharing of electrons. It's these dipoles pulling electrons off of bromine that allows it to pick up that positive charge. So the positive charge is the nucleus of bromine pulling electrons towards itself. Or picking up the positive charge due to the fluorine atoms pulling electrons away from that atom. So positive side, negative side, net dipole moment for ClF3, so this would be a polar molecule. So we also had polar for the BRF5 as well. So nonpolar when all the dipoles are canceling, and then polar when they're not canceling. You can think centers of charge, you can think tug of war is one side of the molecule winning versus the other side. Okay, let's look at a couple structures. The one we've already seen before in terms of the bond angles, we saw that the double bond repels the single bonds more than they repel each other. So instead of the CO molecule being perfectly 120, remember we would have expected 120 from perfect trigonal planar, but we get the greater than 120 due to the double bonds repelling the single bonds more than the single bonds repel each other. So the single bond angles go less than 120. And so then if we have SF6, or excuse me, SF4, the structure here, again, we would have predicted about 120 for this bond angle here from perfect trigonal planar, and it's a little bit less than 120 due to that lone pair interaction. So that lone pair is pushing those bond angles closer together, so that this bond angle here is more like 174 degrees instead of being about 180. So we're kicking that bond angle closer together due to lone pair bond pair interactions being greater or stronger in nature than the bond pair interactions. And this is because these electrons are more spread out. So those electrons are being spread out due to having a nuclei attached, the lone pair closer to the nucleus, so greater repulsion. I just wanted to show you what the bond angles kind of look like. So when we're predicting trigonal planar, bond angles are 90, 180, 120 for, 180 for this bond angle, 120 for this bond angle. They're a couple degrees off. So they're not too far off from where we expect, but they're a couple degrees off due to those lone pair interactions.
So we call that polar.
Yes, so that was one of our polar molecules. In fact, let's do one on our own of SO3. So for a molecule like SO3, this becomes tricky because, one, you have to get the Lewis structure. You have to get the Lewis structure correctly. If we make a mistake in the Lewis structure, we might then give the wrong property for the wrong structure. But hopefully we can get the Lewis structure correct, and then once we have the correct Lewis structure, hopefully we can interpret it correctly to get the proper polarity. So let me let you guys spend maybe 2 minutes trying to work out the Lewis structure for SO3, and then from there trying to get the polarity. For the most part, it doesn't matter if your Lewis structure for this question here satisfies the octet rule or satisfies the formal charge rule. It shouldn't make a difference. If you think it makes a difference, then go with the one you think that makes it easiest to determine the polarity. And then I'll talk afterwards how it really doesn't matter. All right, so do we think the bond is polar in SO3? And if so, why? I guess would be the first question. Because if the molecule doesn't have polar bonds, then the molecule is going to be nonpolar. An example of that might be like a hydrocarbon. Like the CH bond, not particularly polar because neither carbon or hydrogen is very electronegative. Their difference isn't very great. So like CH4, even if we're looking at tetrahedral and forgetting that anything tetrahedral with the same atom is going to be nonpolar anyways. But CH4, even if we come up with some other geometry where it could pick up a dipole moment, would be nonpolar because the bond's not very polar. This bond here is just a nonpolar bond. Now, you might need an electronegativity chart to know that for sure. In fact, it's hard to classify a bond as being polar. Like we're probably better at classifying bonds as being more or less polar in terms of a continuum. But this bond here, not very polar, so I'm just hoping that we see that the molecule is not going to be very polar no matter what the geometry is. But it ends up being exactly zero anyways, just due to being tetrahedral, same atom in all spots, the center of charge is still on the carbon. But when we look at SO3, we might fool ourselves depending on which Lewis structure we look at. This Lewis structure here, it might make the problem easier, but it's not that hard with the other structure either. So this structure I boxed is the formal charge Lewis structure. It's the one that minimizes the magnitudes of formal charge, though it expands the octet of sulfur to do so. I generally think the central atom of sulfur doesn't really do this, so I don't think the structure is all that relevant for looking at SO3, but it really makes it easy to see that we have these dipoles pointing towards the O, and they're all the same. They're all the same bond type. The dipole moments are going to be all the same, and those dipoles are going to exactly cancel each other out. Just like BF3, this molecule should be perfectly trigonal planar, and then also perfectly nonpolar. So just like BF3, so if we get BF3 is nonpolar, hopefully we see that SO3 also is nonpolar despite having polar bonds. So we still have these individual bond dipoles, they just all cancel each other out geometrically like they did in BF3. Now what about this Lewis structure here? What about if we had this Lewis structure that satisfies the octet rule, doesn't minimize magnitudes of formal charge? Well, here we just have to keep in mind the concept of resonance, where we have the double bond can resonate over to here, back onto the O, or it can resonate over to here, and this bond here can go back onto the O. So we can have resonance take place in SO3 that make all those bond types still the same as well. So when we look at SO3, all these bond angles are perfectly 120 degrees exactly. Just like in the double bond structure, you would say, well, one of those angles can't be bigger than the other if all the bonds are exactly the same. BF3 is perfectly 120, so SO3 is also perfectly 120 degree bond angles, and it's exact. So even though you might have a Lewis structure with a double bond and two singles, the real bond orders of all three of those SO bonds are going to be 4/3 bonds if you go with the Lewis structure that satisfies the octet rule. So all these bonds here would be 4 pairs of electrons, the double plus the two singles, shared across those 3 covalent bonds. So we have like 4/3 type bonds across the molecule, all the same. Dipole moments, again, all the same because we have the same bond type, same dipoles, they all cancel, still perfectly nonpolar. So a little bit tricky maybe with SO3 compared to BF3, just because we have the double bond instead of having 3 single bonds. Maybe BF3, this is a little bit easier to see, but it's the same consequence, same result for SO3. So hopefully we're seeing perfectly 120 degree bond angles for BF3, perfectly, polar bonds just like we would expect, but then they all cancel each other out. This molecule is also perfectly nonpolar. So I keep saying like perfectly nonpolar because it's exactly would have a dipole moment of 0. So SO3's dipole moment will be 0, no matter which of the two structures we're looking at.
So which one is better? I mean, the double bond for
Well,
SO3 or resonance?
I mean, there's the best answer I can give you is neither one of those two Lewis structures is quote unquote better. Like one of them satisfies the octet. So if we had a question on the test that said, sketch the Lewis structure of SO3, we'd have to then qualify it as saying, show us the Lewis structure with all the atoms satisfying the octet rule, in which case you'd go with this structure here. Now I've sketched it in a weird way where I just haven't moved the double bonds off. So the right Lewis structure, one of them would be, one double bond and 2 single bonds. Okay? And so that would be the Lewis structure that keeps an octet on sulfur, doesn't expand the octet. And then the Lewis structure that minimizes magnitudes of formal charge, sometimes said to be the formal charge rule. I don't like that wording so much. I would prefer the question to say, sketch the Lewis structure of SO3 that minimizes magnitudes of formal charge, and then that would be this structure over here. So both Lewis structures I think are valid. One of them valid for the octet rule, one of them for minimizing magnitudes of formal charge. Okay. And for the sake of this question, it doesn't matter which one you use. Like I said, I think the bottom one might make it easier to see. Like you might come up with an easier interpretation of the polarity with the bottom structure. And depending on the molecule, you might, pick and choose whether or not you're satisfied. Like if you can keep a bond type with your Lewis structure where all the bonds are the same, then that helps you, I think, assess the polarity easier. Because then you have to think about resonance if not. So if we wanted to keep one double bond, like in this structure here, we just have to picture resonance. So we have to then think about resonance, making all those bonds be exactly the same. Like one of the things that, sometimes, what's a test question that was like this, if this is one of the Lewis structures of SO3, the one that we drew earlier, then what is this bond angle here? And so you may say less than 120, right? You may say 2 singles repel each other more than the double, but you have to consider that all these bonds are really 4/3 order and the same as each other. So this bond angle here should be exactly 120 degrees. And so sometimes you have to interpret a question carefully. It may say this is one of the resonance structures or one of the Lewis structures of SO3 2-. Interpret a bond angle. You have to interpret resonance. Those electron pairs are resonating at all times, leading their bond orders to be the same. So we don't have a double and 2 singles. We really have 3 4/3 bonds that all repel each other exactly the same, hence perfectly 120. For some reason, we like to trick students in chemistry, I hear. I don't know. Okay, so we can also interpret structure from, like I said a few times, that we like to sketch structures in 2 dimensions because it's easier to do. Doesn't take a lot of energy to sketch out a structure for like acetic acid that looks like this here, but we can interpret structure in 3 dimensions from this 2-dimensional structure. So I think one thing we have to have in the back of our mind, if we give you a 2-dimensional Lewis structure, doesn't mean that the structure is as it's given in that 2-dimensional structure. It just means we're being lazy. Okay, in this structure here, I have 4 things on that first carbon. So that first carbon has 4 domains. 4 domains has to go tetrahedral. So these bond angles are actually 109.5 degrees. It doesn't mean in the structure as sketched in 2 dimensions they're 109. They're 90 in the structure as sketched, but in the real molecule they'd be 109.5. Our second carbon atom has 1, 2, 3 domains. So it only has 3 domains, so that goes trigonal planar in terms of its electron domain geometry. And then our oxygen atom has 4 domains. It has 2 lone pairs and then 2 bonds, 2 bonding domains. So that goes back to tetrahedral electron domain. And so if we're thinking about this bond angle here between the COH bond angle, it should be closer to 109.5. Now, a question could be, is that bond angle a little greater than 109.5? Should it be exactly 109.5? Is it going to be a little less than 109.5? Well, we have the lone pair interactions. Let's think about the real structure real quick. So let's actually sketch out what this molecule might look like. So our 3-dimensional shape as interpreted from being tetrahedral. So this would be our first tetrahedral CH3 group to our other carbon here. And then I have to have my double bond, let's put it here. And then I'm going to have the oxygen. And then the hydrogen off of it that's in a bent bond. These lone pairs, one of them's going to be coming out, one of them's going to be going back. So they're going to be sticking out and coming at us. And so this bond angle here, again, we said was 109.5 or close to that. And now do you see here, when we picture the actual structure, I think we can see these lone pairs are going to repel the bond pairs more. And that bond angle is going to be a little less than 109.5. So we could even pick up a little less than 109.5 for that COH bond angle. And the other bond angles, we can even pick up that this bond angle, this single bond with the double bond repelling it more, should be a little less than 120. And the C to double bond O bond angle, this should be a little greater than 120 degrees. So we can pick up some subtleties of structure, and sometimes you can see it a little bit better if you actually sketch the 3-dimensional geometry. So we're saying that the double bond angle, a little bit greater than 120, the single bond angle on that trigonal planar group, a little less than 120.
Why is it 109.5? The carbon and P hydrogen on the left extreme?
So the 109.5 is perfect tetrahedral. So 109.5 is for a perfect tetrahedron. These bond angles here would be about 109.5 degrees. So whenever we have an electron domain geometry tetrahedral, the bond angles would be close to 109.5. Because that's perfect tetrahedral. So like CH4 is 109.5. And so then what about this bond angle here? Do we expect this to be greater, less than, or exactly 109.5? It's actually a little tricky, right? Because we have a carbon on one side, hydrogens on the other. We usually just say this. It's about 109.5. So that'll just mean give or take. And that just kind of depends on, does that carbon repel the hydrogens by more? Hard to tell. So we're not really assessing single bond repulsions and breaking those down. So we usually just say, oh, it'll be close to 109.5. Okay, so then we can also give structures like this here where we actually come up with the Lewis structure. Now, how do we come up with the Lewis structure for something like CH2, CH, CH? Well, one of the ways could be that we just literally start sketching out like our CH2, then I go to CH, then I go to a C, and then I go to another C, then I go to an H. Because I'm just interpreting this structure linearly as the atoms are given. So CH2, CH, C, CH. And so then I can sort of count electrons. So I might start counting up my electrons for each of the carbons. I have 1, 2, 3, 4 carbons. So that's 4 times 4 plus the hydrogens. I have 4 hydrogens. So that should be 20 electrons. So I've only used 2, 4, 6, 8, 10, 12, 14 electrons. So I've used 14. I have 6 electrons left to go. And so now I could do lone pairs, but remember how carbon wants to form 4 bonds, like CH4 has 4 bonds, CO, like if you look at this structure, let me erase a little bit up here. So if we look at like this carbon here, we have 1, 2, 3, 4 bonds, just a double bond, 2 single arrangement. So carbon wants to form 4 bonds. If we take advantage of that, I go double, so that uses 2 of those electrons, and then I go triple over here, and that uses the remaining 4, so I have none left over. And by coming up with those bond types, so by coming up with a prototype for carbon in a stable molecule where it has 4 bonds, no lone pairs, kicks me into this geometry pretty quickly. So then each of my carbons has one, let me use this pointer here. So I have 1, 2, 3, 4 bonds, 1, 2, 3, 4 bonds about the second carbon. The third carbon has 1, 2, 3, 4 bonds about it. And then the last carbon has 1, 2, 3, 4 bonds as well. Okay, so that gets me 4 bonds for all the carbon atoms. And so then from there, or from this Lewis structure, we can start to assess our structure, whether or not we start to re-sketch the molecule. In some ways, I've already kind of put some of the key bond angles in. These are about 120. So which angle do you think is greater than 120 here? Probably the double bond, single bond. So probably a little greater here, and that single bond angle a little lesser than 120. And so the same thing here, 120, 120, and then 120. And again, a little less than 120 for that single bond, a little greater than 120 for the double bond, single bond angle. And then I get these 2 angles here, both of which have to be perfectly 180. Because I have a triple bond, that single bond has to get as far away from it as possible, so that goes 180. And these will be exactly 180. There's really no way, because if they go less than 180, then it's too close to the triple bond, so it goes back to 180. So if it tries to go the other direction, it's less than 180 as well, so it has to stay perfectly 180. And so then we can sort of look for if we go carbon 1, carbon 2, let's just go through the 3 carbons to fill in a chart here. So like carbon 1 is trigonal planar. So carbon 1 is trigonal planar. Bond angles of about 120 degrees. Our second one was also trigonal planar, also close to 120. And our third and fourth atoms, so these 2 here, are linear. With 180 degrees.
What is linear? Why is 3 linear?
So 3 has 1, 2 domains. A triple bond is just 1 domain. So yeah, so it's sort of like bonding pairs. So we have 1 set of bonds on one side, 1 set of bonds on the other, and then just like CO2 goes 180, that linear group goes 180 as well. And so then the next carbon, again, 1 and then 2 domains. Let me see, wrong button. Actually do another molecule or 2 in terms of sketching a Lewis structure. Like if we need to do, let's just go back to like an alcohol. In some cases we might remember these as well, but we might say, well, how do you come up with the Lewis structure for an alcohol when you have a formula given to you like CH3, CH2, OH? Well, we would just interpret the CH3, the CH2 with these hydrogens attached in that fashion, and then the OH group here. And then again, like trying to figure out for oxygen, its number of electron pairs, we could count, so that's one thing we could do is we could count up the 2 carbons, so that's 2 times 4 to come up with our valence count. Then we need the oxygen for 6, and then we need 6 hydrogens times 1. So that's also 20 electrons. It's for 8 plus 6 plus 6, yep. So 20 electrons total, and so far I've distributed 2, 4, 6, 8, 10, 12, 14, 16. So I have 4 electrons left to go. Now you may say, well, the last structure I made double bonds. Should I like do this? And I think you can see right away why I don't do that. I don't do that because it gives carbon way too many electrons. It gives this carbon here 2, 4, 6, 8, 10, 12 electrons surrounding it. That carbon had its 4 bonds that it wanted. So carbon only wants to form 4 bonds, so this carbon's good here, so this is why we would go lone pairs. So we kick lone pairs onto the oxygens, that kicks us down to having no electrons left over. And so this would be the Lewis structure for ethanol. Now let's do one. Yeah. So let's look at SP. Well, okay, that's the wrong thing. Or we'll get to that in a minute. But this will be tetrahedral because it has 4 domains. This will be tetrahedral as well because it has 4 domains, and the oxygen as well. So all 3 of our centers here are tetrahedral because they each have 4 domains. Okay, and so then the bond angle here will be bent if we think about like the actual geometry name, because 2 lone pairs, 2 bond pairs like water, that's going to be a bent bond angle. So it'll be less than 109.5 degrees. And then our bond angles here about 109.5 degrees for the other bond angles across the molecule. Yeah?
I thought from the first chart, we ignore the lone pair when we are naming the shape of the bond. So the last oxygen should be linear.
No, we don't ignore, like the electron pairs still give the molecule its shape. We just ignore them from the name of the shape. Okay, so.
Ignoring the name of the shape, and the last one will be linear.
No. So the thing about water. So is water perfectly 180? The answer is no, it's not perfectly 180. So for water, we have to think that all those domains still fit being tetrahedral because we have 4 things. It's just we have lone pairs on 2 of the spots. We have hydrogens on the other. And so then the molecule here, the bond angle is not, to be linear would mean it has to be 180 degrees. So to be linear means 180, but you can see here that this bond angle has to be closer to that tetrahedral bond angle of 109.5. And again, lone pair repulsions kick it to be a little less than 109.5. And so then when we name water as being bent, the name, we just look at the atoms. Now the electron pairs, they're still there. They still give the molecule its shape, but we just don't consider them for the shape name. So the molecular geometry name just says, look at the atoms. What's the geometry? What's the best name we can give the shape of those atoms? The lone pairs are still there, so it's not like they disappear and it goes back to a different structure. Where we look at a nitrogen group, so let's do CH3.
Can we do the bond groups for the previous?
Let's do CH3CN just to do an example with a nitrogen atom. And let's even do a second one, CH3NH2. So both of these are actually pretty common molecules. So CH3CN, pretty easy for the CH3. Then our C to our N goes like this. And then if we count our electrons, we have 8 plus 3 plus 5. So that's 16 electrons. I've distributed 2, 4, 6, 8, 10 electrons. So then if I go with the idea carbon should have 4 bonds, so a triple bond to the CN gives carbon with 4 bonds, and then that uses up, of the 6 electrons we had left over, that uses 4 of them. So the 2 remaining electrons can go on to nitrogen. Now, there's another way we could have ended up with this structure here. So you may say, well, how do you know, or like, what if we had done the actual Lewis structure rule? Remember, like the non-central atoms get an octet, and then you would think of your charge here being 2 plus, and then we can make 1 double bond to kick this down to plus. Then we can make a second double bond to kick that down to 0. So you could get to that structure a couple of different ways, where you see a lone pair on nitrogen, and then 3 bonds in terms of a triple bond. So all of our atoms here satisfying the octet rule. All the atoms also have a 0 formal charge all the way around. So carbon forms 4 bonds, no lone pairs. That gives it an octet and a 0 formal charge. Nitrogen tends to form a 3 bonds and a lone pair. That gives it a 0 formal charge, also an octet. We saw in the previous example, like with water, 2 bonds, 2 lone pairs gives an oxygen atom, an octet, and a 0 formal charge. And so for the last one on this sheet here, our CH3NH2. So hydrogen, 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 NH2, then we might count. If we count, we get 4 plus 3 plus 5 plus 2. So that's 9 plus 5, that's 14 electrons. So for 14 electrons, 2, 4, 6, 8, 10, 12. And so then our leftover electrons, let's put them on our only open octet on nitrogen for a lone pair. So the nitrogen here has 1, 2, 3 bonds in a lone pair, hence a 0 formal charge. All the atoms here have 0 formal charges. Okay, so carbon, 4 bonds, no lone pairs. Nitrogen, 3 bonds in a lone pair. Oxygen, 2 bonds in a lone pair. And if you go back to like HF, fluorine, the halogen group would form 3 lone pairs and a lone pair. Or excuse me, 3 lone pairs and a bond pair will give it a 0 formal charge. So you can come up with Lewis structures of organic molecules. In fact, all of OChem will be sketching all kinds of Lewis structures. And if you just always come back to the idea of don't put 5 bonds on carbon, and that's like a golden rule for OChem for a stable molecule, and you'll be well off. And generally not 3. It can have 3 and maybe like a mechanism or some kind of sometimes in organic chemistry, you write how does one molecule react to form some other molecule. You'll have some goofy structures along the way of a reaction mechanism. But for a stable molecule, it should have 4 bonds to carbon, 3 to nitrogen, 2 to oxygen. Yeah, so the bond shapes here, again, tetrahedral for the CH3s. And then what do you say for this carbon here? Linear, right? Because it has 1, 2 domains. So just the triple bond's just one domain. So one set of electrons on one side of carbon, another set of electrons on the other. So perfectly 180. And the nitrogen as well. So the nitrogen atom's also linear. What about this structure here? Well, each the nitrogen and the carbon here have 4 domains, so that's tetrahedral. I keep wanting to write sp3. You're going to see in a little bit why I want to write sp3. So a bonding model will show, like we'll see in a minute. You may have seen it in high school as an sp3 bonding model, but we'll talk about that in a minute. So tetrahedral, 4 domains, 109.5 degrees. And then the only angle that's maybe a little bit interesting here is the carbon to nitrogen to hydrogen angle will be a little less than 109.5. So this bond angle here, due to the lone pair repulsion, is a little less than 109.5 degrees. And the same thing with the other nitrogen-centered bond angles. Okay. Daily quizzes have a bunch of questions on structure, interpreting shape, interpreting polarity. So look at those for this week. They'll have a ton of examples of polarity, structure, bond angles, geometry names so that we're getting these down pat. So it usually starts from correct Lewis structure to correct shape, and then you're good to go. If we have a wrong Lewis structure, it's going to be hard to get the shape correct. So getting a good Lewis structure, hopefully we're just reinforcing Lewis structures here in chapter 9 from chapter 8. So let's talk about like how bonds are made in some different bonding models. And so one of the bonding models says that bonds form just from the overlap of orbitals. So like a hydrogen-hydrogen bond forms from the overlap of the 2 electrons that they each have and their 1s orbital. So if you think of one of the hydrogens having an electron, let me sketch this over here. So if you imagine a hydrogen here has an electron spinning around its nucleus, and then it pairs up with another hydrogen with its electron spinning around its nucleus, that they can just pair their spins together and the orbitals just overlap. So the overlap of atomic orbitals leading to molecular orbitals is one bonding model. Now, if we look at sort of a diagram for hydrogen, let me zoom in on this. So for hydrogen, at far separation, if we keep separating the atoms, they have no relative energy. So they just are at 0 energy when they're far separated. We start bringing the atoms closer together, their energy starts to drop because their orbitals are overlapping. Each of the electrons experiences an attraction to the other nuclei. And so as we drop down to the most stable bond length for hydrogen, which happens to be about 0.74 angstrom, that's where the 2 electrons here are sort of maxing out their attraction for the other nuclei while minimizing the repulsions they have with each other and the nuclear repulsions. So if we keep pressing the bonding, it'll be too close together, the energy goes back up because of nuclear repulsions. So if we keep compressing the bond angle past the ideal bond length, we get nuclear-nuclear repulsions. So that leads to the increase in energy there. So that's just the nuclei of the atoms repelling each other. And then the reason why we get the drop in energy here, so the reason why we get the drop is because of the electron nuclear attraction. So the electrons in the bond are being mutually attracted to both nuclei. And so the electrons are pulling the nuclei together. And again, it reaches like a happy point, if you will. So every bond has an ideal bond length. Like a CH, carbon's bigger than hydrogen, so the CH bond length's a little bit longer. And so the CH bond length would be a little bit longer in terms of its ideal bond distance. And so you can imagine that for like HCl, you can say, well, we could describe this bond here by thinking, well, what's the highest energy orbital of chlorine? So you think chlorine has a 3s, let me rewrite this, a 3s2, 3p5 configuration. So the biggest orbital would be the p orbital. And so we might think, okay, if we're going to have HCl, that this bond here should be the biggest orbital of hydrogen, the 1s, then the biggest orbital of chlorine, a 3p. So the bond between HCl would be the 1s 3p overlap to make that single bond. Then if you had two chlorines overlapping with each other, you would say, well, okay, it's just the biggest atom. So we have the p orbital of the one chlorine, the p orbital of the other. So we have the 3p overlap making up the Cl2 bond length. And so chlorines are bigger than hydrogen, so the Cl ideal bond length is going to be longer than the HCl bond length. That's going to be longer than the HH bond length. So we can even sort of predict kind of what we already know, that the bond length of H2 is going to be shorter than in HCl, which is going to be shorter than in Cl2. Just as those atoms are growing in size, their overlap is growing to be at a longer distance of separation of those nuclei. So again, if we try to go chlorine past its ideal bond length, the nuclei, relatively highly charged, starts to repel each other and dominate the energy would go upwards. And so then, how do we get overlap when we look at an atom and we have to get like two sets of bonds? So like if I look at beryllium here and say, well, how do I get overlap when beryllium really just has like an s orbital? Like, so how can one orbital bond with two different things at the same time? Well, the answer is that what it's going to do is it's going to find a way to use its other orbitals. So what if beryllium says, okay, so beryllium has a 2s2 configuration. It's in the second row. It's just right next to lithium. So its configuration is a 2s2. And it's going to be hard for one orbital to simultaneously overlap with two other orbitals from the other two fluorine atoms. So what if instead we say, well, what if we take a 2s and a 2p and mix them together on the beryllium atom? So what if I take an s orbital and a p orbital, and I mix them together, and I kind of come up with orbital 1 over here and orbital 2 over here. So in order to come up with two different orbitals, so I call these the two hybrid orbitals, I have to start with two atomic orbitals. So I get two hybrid orbitals. I need to start with two atomic orbitals. And then this process here is this is a bonding model. This doesn't really mean that the orbitals really do this necessarily, but it's just a model for trying to understand the orbitals for beryllium is to say, if I need to make two bonds on either side of beryllium, where I only see one orbital from its electron configuration, what I need to do is just do some mixing. So what I do is I mix an S and a P on beryllium, and then they mix together, hybridize, and form two different orbitals, one this way, so that's orbital 1, and orbital 2 this way. And then that allows me to get my overlap with fluorine. Fluorine being a 2p with its largest orbital, so I would get 2p, then I call this sp overlap. So what we call beryllium here is sp hybridized. So this is sp hybridization, where I hybridize one s and one p on beryllium. Hold on a second. So we call those sp hybrid orbitals from the mixing of one of the s, one of the p's on beryllium. This we're not even thinking polarity yet. We haven't even gone as far as thinking about the polarity. We can think about polarity in this is a linear bond. So beryllium's with fluorine on either side, the molecule has to be nonpolar. So if we think about the polarity, if you have beryllium, 2 fluorines opposing it, perfectly 180, because there's no lone pairs on beryllium, we could even take a step back and say, okay, let's take a step back. Beryllium has 2 electrons, the fluorines have 7 each, 16 electrons. So our Lewis structure is this one. And we leave beryllium deficient of an octet, just like we left boron deficient of an octet in BF3. So we leave beryllium deficient of an octet because it has a 0 formal charge. Okay, so just making sure we see our Lewis structure here has beryllium, no electrons on it, 2 fluorines, so it's going to be linear in its structure, so perfectly 180. So perfectly 180 degree bond angle. And then the question becomes, well, how do you describe that bond? Like we described Cl2 as 3p overlap, fluorine's 2p, so we're going to have 2p overlap of fluorine, but with what on beryllium? And so that's where we came up with the problem of beryllium only has 1 orbital, one orbital can overlap with one other orbital. So how do we get another orbital to overlap with the other fluorine? The answer is we change our bonding model. We say, let's take an S and a P of beryllium and mix them together and then create 1 orbital this way and 1 orbital this way. So that's our sp hybrid orbitals. So again, take an S. So instead of having 2 electrons in a 2s orbital, we say let's put 1 electron in an sp orbital and another electron in an sp orbital. And so here we have an electron here to overlap with the electron in that 2p orbital of fluorine. Okay, so if I'm looking at beryllium, I would say that the bond here would be our 2p of fluorine and then the sp, so I get 2p sp overlap. So 2p on fluorine, sp on beryllium. Now, as we continue, this might make more sense. Maybe it'll make less sense. I don't know. We'll see. But I think it'll make more sense because as soon as you see the next one, then maybe you'll see where we're going with this. Boron has, if you just say, okay, boron F3, making sure we see the Lewis structure, 3 single bonds, perfectly 120 degree bond angles, trigonal planar structure. The question becomes, how do we describe the bond? So how do we describe the bond when boron's configuration is a 2s2, 2p1? So again, I have kind of the problem of I have 2 orbitals, but I really need 3. So I need 3 orbitals on boron. Why do I need 3? Well, each orbital should be able to overlap with fluorine. So I need to make 3 orbitals somehow on boron. How do I do this? Well, the answer is kind of voodoo math in a way. What we do is we say, well, what does boron have available? Boron has 2p orbitals. We only have that 1 2s orbital. So we take the 2s orbital, and then we mix it with 2 of the p orbitals of boron. Okay, so we're going to take an s plus p plus p. So we take s plus p plus p. We call that sp2 for having 2 of the p orbitals hybridized instead of just 1. Okay, now mathematically or geometrically or however you're seeing this, we're going to take the p orbitals of boron that are in the plane of the fluorines, and we're going to leave behind. There's 1 p orbital we're not using, but that's okay. So we're going to leave an unhybridized p orbital. That's going to be the one sticking straight out of the page. So we still have a p orbital left over. Some structures we'll see, probably not today, probably on Wednesday, we'll see that some atoms can actually use that extra orbital to make a double bond. But so we take the s and then these p orbitals here, mix them together. So take 3 orbitals in, get 3 new orbitals out, and they're going to point in the direction of the trigonal planar structure of 120 degree bond angles. Like I said, this is voodoo math. This isn't real math. This is just a model for understanding the bond of boron. So we say boron here is sp2 hybridized. So then you get sp2, 2p overlap. So this model here, we call this hybrid orbital theory. It's saying if we know bonds are made from overlap of orbitals, if I don't have orbitals where I need them, I hybridize them to be where I need them. And so I just say if I need 3 orbitals, I need to hybridize 3 atomic orbitals. So 3 AOs, 3 atomic orbitals, are mixed into 3 hybrid orbitals. And we just look at our domain geometry. So trigonal planar, 3 domains, needs to go trigonal planar. 2 domains needs to go linear, SP hybridization. Okay, so where do you think we go next? So where do you think we go with 4 domains? Well, for 4 domains, we're going to be SP3. So when I look at CCL4, we might remember it has a tetrahedral geometry, 109.5 degree angles. We have 4 domains. Having 4 domains means I need 4 orbitals. So if I need 4 hybrid orbitals, how many atomic orbitals do I need to start with? So if I start with 4 atomic orbitals, those can hybridize into 4 hybrid orbitals. And so then if you start thinking of carbons in the second row, so the full second row is the 2s, 2px, 2py, 2pz. So again, this is voodoo math. This isn't like real math. This is a model. So we take 3 of the p orbitals with the 1s, we mix them together, we get 4 orbitals pointing in the direction where we need them, in the direction of a tetrahedron. So we call this sp3 hybridization. So tetrahedral structures, tetrahedral electron domain goes sp3, trigonal planar goes sp2, linear goes sp. And in some regard, this is almost redundant in a way, because it's really just saying if you know electron domain, like for water, for example, that water would be sp3 hybridized on that oxygen. So we have 4 orbitals pointing in the direction of a tetrahedron. And so then you can describe for water, you would say for water, you have oxygen, lone pairs, the bonds to hydrogen, that you can picture these electrons in some sort of orbital, maybe in an sp3 orbital. So oxygen here, you're going to say sp3 hybridized. So the hydrogen-oxygen bond angle, or the hydrogen-oxygen bond, you could say, is the result of 1s sp3 overlap. So you can start to describe what that bond looks like by thinking of the hybridization of the central atom from the structure of the molecule being tetrahedral. So tetrahedral is sp3. CCl4, tetrahedral, so it goes sp3. So orbital 1, 2, 3, 4. So we're describing these bonds here as being sp3, 3p. So 3p for chlorine, because chlorine's biggest orbital is a 3p, and then carbon would go sp3. Yeah.
I was just gonna ask, where are you getting like 3p or like the mass?
Yeah. So it just comes from, so atoms like carbon has 2s2, 2p2 configuration just as a normal atom. And so then if you're thinking of our diagram here, you're thinking this configuration. And so sp3 says, well, what if we mix all these orbitals together here? So you have the 2s and then the 3 2p's. And so where you get sp3 from is just using that extra p orbital. And so then you only ever have one s. So you can't have like s2p3, right? So there's only one s orbital on those central atoms.
But the chlorine is, they are not 3 pairs. 3 p's are not 3 pairs. The last one is
Chlorine, you think of its biggest orbital. So chlorine's just a single atom. So you just think for chlorine, its biggest orbital is a 3p. So it kind of goes back to the very first slide where we had hydrogen, hydrogen, 1s, 1s, hydrogen, chlorine, 1s, 3p, chlorine, chlorine, 3p, 3p. So the chlorine's good with a 3p. We could think chlorine's sp3 as well, but we could think chlorine just uses its biggest orbital. Its biggest orbital being a 3p orbital, overlapping with an sp3. Let me show you, the next thing that we're going to see is like the leftover orbitals that aren't hybridized. Like if you look at the 2 carbons here, they're sp2, right? Or excuse me, they're trigonal planar for sure from what we have seen before. So trigonal planar is sp2. And sp2 leaves behind a p orbital, and that p orbital left over can make that pi bond. So where we're going to go with this is describing pi bonds as overlapping p orbitals and making a bond that's sort of planar in nature. And most of our single bonds are kind of symmetrical about the bond axis in nature. We call those sigma bonds. So we're going to talk as we go about sigma bonds versus pi bonds. So pi bonds are kind of planar bonds. Sigma bonds are like bond axis symmetrical bonds. So that's where we'll pick up on Wednesday, and we'll continue. Let me just allude to one other thing. Is we're going to finish our chapter 9 discussion on these like sort of molecular orbital diagrams. So we're going to start to see how like diatomic molecules overlap orbitals into these types of diagrams. So that's where we'll finish up on Wednesday to wrap chapter 9 up. Test next Wednesday is over chapters 7 through 9. So Friday is a holiday, just look ahead. So Wednesday is our last content lecture. Next Monday and Wednesday, review lectures. Okay, guys, have a great day. You can't draw two double bonds because that would expand the outside of oxygen, and so it doesn't have room for those two extra electrons. So you notice how oxygen has 8 electrons surrounding it? So that's the max oxygen can have. And so then we can resonate an electron pair, so we can move an electron to make a double bond, but this has to go back to single. And so then through resonance, yeah. Yeah. Yep.
Hi, so I don't understand how CH is not polar and SO is polar.
Well, I think the CH, like difference of electron activity is pretty small. It's like 0.4. I think
Okay.
the SO difference is like either a difference of half or about 1.
Okay, but I would think that the CH was more polar because they're so much farther apart.
Oh, it's like I said, it's a trick without an electronegativity chart. I don't know if we could say that for sure. So I think you'd almost have to go back to an electronegativity chart to see how different they are.
So are we gonna get that on the exam?
Well, I don't think we would ask that. Like, I don't think we would say is the CH bond polar or non-polar. But I was trying to think of an example of a molecule that would just be non-polar by virtue of having non-polar bonds, if you knew that. So that there will be some molecules that just the atoms just don't have a great difference in electronegativity, so the molecule wouldn't be polar as a result.
Right, that I understand. I just don't get why this one is not polar and this one is still.
Well, I mean, I think we just have to go back to an electronegativity chart.
Right, but